Welcome to the 23rd video in the series of research methodology titled Probability/Randomized Sampling Methods. So I want you to imagine, just for a second, trying to ask every single person in your entire country what their absolute favorite food is. I mean, going door to door to millions of people. It's completely impossible, right? Well, this right here is the fundamental problem in any kind of research. It is almost always literally impossible to study every single member of a population, whether that population is just too massively large, too widely distributed geographically, or frankly just way too expensive to reach. We simply cannot survey everyone. And because of this reality, we researchers have to rely on selecting a smaller group. We call this a sample. We collect data from them to hopefully uncover the truth about the wider population. But here is the million-dollar question. How do we make sure this smaller group actually represents the whole, without our own personal biases getting in the way? How do we know we aren't accidentally just asking our friends or people who happen to live in our neighborhood? Well, that objective, scientifically sound selection process is exactly what we're going to master today.
Okay, let's dive right into this. Here is our roadmap for how we're going to systematically break down the researcher's toolkit today. First, we'll cover the basics of probability sampling. Then we'll look at simple and systematic sampling, followed by stratified random sampling. After that, we'll scale things up with cluster and multi-stage sampling. Finally, we'll wrap up by looking at general strengths and limits, and, of course, the ethics in random sampling.
Let's start right at the top with Part 1, the basics of probability sampling. This is the core concept that really anchors this entire explainer.
At its absolute heart, probability sampling, which you might also hear called unbiased or randomized sampling, is a selection method where every single unit of the population has a known non-zero chance of being included. Now that sounds a bit academic, but all it really means is that the selection is based entirely on chance, not on convenience, not on who the researcher happens to bump into, and definitely not on personal judgment. For example, if a university has exactly 5,000 students and we want to select 500 of them using a computer-generated random number system, well, every single student had a known mathematical chance of being picked. But for this to actually work in the real world, you absolutely need two mandatory ingredients. First, you need a clearly defined population. You can't just say, I'm studying students. Actually, scratch that. You could, but it would be terrible research. You have to specify something like undergraduate students in Dehradun district. Second, and this is absolutely crucial, you need a sampling frame. A sampling frame is the actual physical list you are drawing your names from. Think of a voter list or an official school register. This is where so much research goes completely off the rails. If your school register is from last year, well, you are completely excluding all the newly enrolled students. Because your list is incomplete, your entire sample is instantly biased from day one. Now that we have that basic definition locked in, let's move to Part 2. We're going to introduce the two most foundational tools in the methodology toolkit: simple and systematic sampling. First up, we have simple random sampling. This is the purest, most basic form of chance selection. Think of it like a giant, perfectly mixed lottery drum. In this method, every single member of the population has an equal and independent chance of being selected. When we say equal, we mean no one has an unfair advantage. And independent means picking one person doesn't magically affect the chances of picking someone else. Imagine having a computer randomly pick 100 students out of a population of 1,000. It is beautifully transparent, it's incredibly easy to explain to your audience, and it is phenomenally effective at reducing a researcher's own personal bias. Because it's just so mathematically sound, it brilliantly supports advanced statistical analysis later down the line. However, it's not perfect. Like we just talked about, it absolutely requires that complete sampling frame. If your list is missing people, the whole thing falls apart. And importantly, if you have a very small minority subgroup in your population, pure chance might mean they accidentally get missed entirely just by the luck of the draw.
Next up is systematic random sampling. Now, what's really interesting about this one is how incredibly procedural it gets. Instead of relying purely on a random number generator for every single pick, you use a highly structured mathematical system. Let's walk through the steps. Step 1, you divide your total population size by your desired sample size, and that gives you your sampling interval. For example, if you have a list of 1,000 teachers and you know you want a sample of 100, you simply divide 1,000 by 100. That gives you an interval of 10. Simple enough, right? Step 2, you pick a random starting point between 1 and 10. Let's say you roll a die and you get a 6. Step 3, you just apply your interval. You select the 6th teacher on the list, then the 16th, the 26th, the 36th, and so on until you reach your 100 people. It is so much quicker to implement and highly practical for field surveys. It's basically like walking down a street and deciding you're going to knock on every 5th door. So let's contrast these two directly, because researchers use both all the time. Simple random sampling relies purely on chance for every single pick. This makes it highly objective and randomized. Systematic random sampling, on the other hand, is much quicker and far easier to administer, especially if you are dealing with very, very long physical lists. But systematic sampling introduces a real danger, a fatal flaw that even seasoned researchers sometimes fall into. It's known as periodicity. Periodicity refers to hidden patterns lurking within your sampling frame. Imagine your master list of students is organized by class section, and it just so happens that every 10th name is the top performing student in that specific section. If your interval lands on that hidden pattern, you are going to accidentally pick a sample made up entirely of top performers. That would completely wreck the representativeness of your data and give you wildly skewed results.
So what do we do when our population is heavily divided or heterogeneous, and we absolutely cannot afford to miss a subgroup? That brings us to part 3, stratified random sampling.
The absolute best solution for a highly divided population is stratified random sampling. Basically, you take your entire population and you actively divide it into distinct, non-overlapping subgroups. We call these subgroups strata, and you base them on really important characteristics. For example, let's say our population is schools. We could divide them by type, 50% government, 30% private, and 20% rural. Once you have them neatly divided, you then pull a random sample out of each specific slice of the pie. By doing this, you mathematically guarantee that minority or smaller groups, like those 20% rural schools, aren't accidentally missed by the luck of the draw, which, as we know, can definitely happen in simple random sampling. It vastly improves the accuracy and credibility of your findings, and it allows you to directly compare different subgroups against each other. The major catch here? Well, you need incredibly detailed upfront knowledge about your population to be able to divide them correctly into these strata in the first place. If you don't know the exact percentages beforehand, you can't build the strata.
But what if your population is simply too massive and too geographically spread out to ever list everyone out? Let's shift our focus to part 4, cluster and multi-stage sampling. When researchers need to tackle massive, scattered populations without completely breaking the bank, they turn to these two methods. Let's compare them. With cluster sampling, instead of randomly picking individual students across an entire state, which would be a logistical nightmare, you randomly pick natural groups or clusters, think specific schools or entire villages. Then you study the individuals inside those selected clusters. The big advantage here is obvious. It is highly economical and saves an absolute ton of travel time and resources. The limitation? You get high sampling error. Why? Because students in the same school tend to be fairly similar in socioeconomic background, which naturally reduces the overall diversity of your data. Then we have multi-stage sampling. I like to think of this one like those Russian nesting dolls. You literally select units in stages. So for a massive national survey in a country as big as India, you might randomly select states first. Then you open that doll and randomly select districts within those states. Then schools within those districts, and finally, students within those schools. It is absolutely perfect for vast, complex national surveys. But the trade-off? It's immensely complex to design, and there is a real mathematical reality that sampling errors can actually compound every single stage of the process. Okay, let's zoom out for a second and examine the big picture of quantitative probability sampling as a whole in Part 5, General Strengths and Limits. I actually want to pose this question directly to you, especially looking at everything we've covered so far. Does random selection automatically guarantee perfect accuracy? I actually want to pose this question directly to you, especially looking at everything we've covered so far.
Does random selection automatically guarantee perfect accuracy? I'll give you a second. The answer is absolutely not. No way. Being unbiased does not mean being error-free. It simply means the procedure doesn't systematically favor one group over another. So the crucial point to take away here is that even the absolute most rigorous random sampling has hard limits. First off, it completely falls apart without an accurate, complete sampling frame. If you are studying migrant workers or informal laborers, a complete up-to-date list likely doesn't even exist anywhere. That makes these methods almost impossible to use. Second, doing this properly can be incredibly expensive and time-consuming to execute. Third, and this is a big one, there is non-response bias. Even if your computer perfectly and randomly selects a participant, they can just refuse to participate. For instance, imagine you randomly select 100 people to take a survey on some brand new technology. But if the elderly participants consistently refuse to take it because it's an online-only survey, well, your data is now completely skewed toward a younger demographic, despite your quote-unquote perfect random selection. Furthermore, random sampling does absolutely nothing to eliminate measurement bias or poorly written survey questions. And lastly, it's just not always suitable for in-depth qualitative research. Sometimes you want depth, emotion, and deep meaning from purposefully selected individuals, rather than just broad statistical representation.
As we approach the end of our explainer today, we must transition to part 6, covering the moral imperatives that bind all legitimate researchers: ethics in random sampling. You see, sampling isn't just some cold, detached mathematical procedure. We are dealing with real human beings here. As the foundational Belmont Report outlines, all research must be guided by respect for persons, beneficence, and justice. Now, definitely don't want to get preachy, but what this means in practical terms is that random selection never overrides human rights. You cannot force a randomly selected person to participate just because your fancy computer algorithm chose their name. Informed consent is absolutely mandatory every single time. Privacy and confidentiality must be fiercely protected. Furthermore, the principle of justice dictates that we have to avoid unfairly burdening certain vulnerable groups with our research while excluding others from the potential benefits. Good ethical sampling always demands fairness, open communication, and absolute transparency with your participants from start to finish.
To wrap all of this up, remember this golden rule. No sampling method is perfect. Whether it's simple, systematic, stratified, cluster, or multi-stage, the real key is matching the right tool to your specific research problem, the unique structure of your population, and of course, your available resources. Understanding both the brilliant strengths and fatal flaws of these tools is exactly what makes a strong, capable researcher. I want to leave you with a final provocative thought today. If you had to survey your own local community tomorrow on a highly sensitive topic, which of these methods would you trust the most to avoid bias? Really think about it. Thank you so much for joining me today for this deep dive. If you found this explainer helpful, please make sure to like, comment, share, and subscribe to this channel for more clear, structured, and visually driven research methodologies. I'll see you in the next one.